When we differentiate our trig functions, we go to our formula sheet and tan differentiates to secant squared. The angle part, in this case x squared plus 2, will stay the same. So tan x squared plus 2 becomes secant squared x squared plus 2. And then, as always, we differentiate the expression for x. And so x squared gives times 2x. 2x secant squared x squared plus 2. To find the gradient, we have to differentiate and then put our value of x equals 1 into that gradient equation. To differentiate e to the 1 over x, differentiating e always stays exactly the same. So we still have e to the 1 over x in our answer. But see over there on the right hand side in that sort of yellow box, when you differentiate the 1 over x, or x to the negative 1, you get negative 1 x to the negative 2, which is equivalent to negative 1 over x squared. So our gradient function is negative 1 over x squared e to the 1 over x. When I put 1 into that for x, it simplifies down just to negative e, or from our calculator, negative 2.718. Question C, a merit question. It starts off the same as question B did, so we firstly have to differentiate our expression e to the negative x times sine x, a product rule question. Write down the first, differentiate the second, plus write down the second, differentiate the first. So our gradient function dy dx equals e to the negative x cos x minus e to the negative x sine x. Now, if I'm trying to find a minimum point, I need to know where the gradient equals 0. So my gradient function equals 0, and to solve that, I start by taking e to the negative x out as a common factor. Now, when you've got brackets like this, it's the same as we've done earlier with solving quadratics, either the first part equals 0 or the second part. In this case, e to the negative x equals 0, well, that actually can't happen, or the bracket cos x minus sine x equals 0. If cos x equals sine x, one of the facts we should know is this 45-degree triangle, that cos 45 equals sine 45, and so for our answer here, cos x equals sine x equals 45, or in terms of pi, it's pi over 4. Now we know x equals pi over 4. To find our value of y, we need to substitute pi over 4 back up here in the original question, where y equals e to the negative x sine x. Putting pi over 4 in there gives the decimal value 0.3224. So that's the value of our stationary point, and now we need to determine if it's a maximum minimum point. The maximum minimum comes from that second derivative test. So my first step is to differentiate the first derivative again, and that simplifies down to negative 2e to the negative x cos x. Our test is that if that's less than 0, it's a maximum point, and if it's greater than 0, it's a minimum point. Putting x equals pi over 4 into the second derivative gave a negative answer, and hence my coordinate is a maximum. When we're differentiating parametric equations, we use that chain rule I have there in the yellow box. dy dx equals dt dx times dy dt. So I've got x equals 1 over t minus 1, which you can see there in the other yellow box is t minus 1, the negative 1. When that's differentiated, the negative 1 comes out the front, and you get negative 1 t minus 1 in brackets power of negative 2. Or as I've written there in my working, negative 1 over t minus 1 squared. And y equals t squared minus 2t, differentiating dy dt 2t minus 2. To put those two bits into the chain rule, when I've differentiated, I've got dx dt, and in my chain rule it says dt dx, so I need the reciprocal. So I'm going to turn that up the other way and become negative t minus 2 squared. Now, to find the gradient of my parametric equations, I've got three little bits of working on the right hand side in yellow that I'm going to have to refer to. X is 1 over t minus 1, and so that becomes t minus 1 to the negative 1. I'm asked to find dy dx, and I'll need the chain rule. Dy dx equals dt dx times dx dt. And when I come to differentiate dy dt, which is 2t minus 2, I'm going to take the 2 out as a common factor and have 2 times t minus 1 and see how they all fit together. So I've done the dy dt and the dt dx. So here I am there on the left, dy dt, 2t minus 2, and dx dt is negative 1 over t minus 1 squared. Notice I'm going to use the reciprocal of that in my chain rule, and it'll become negative t minus 1 squared. So dy dx is going to be 2 brackets t minus 1, and divided by dx dt, or times the reciprocal, dt dx, and that ends up giving negative 2 t minus 1 cubed. The gradient, when t equals 2, well, we just put 2 in place of the letter t, and the gradient comes out negative 2. This excellence question I'll need to go through in more detail individually in class. The key though is when you're looking at it, it's got a box, has a square base. So the base is x times x. We don't know the height, so it's not x, it's some other variable, and we'll call it h. Volume is base times height, x squared h. And the surface area comes out as you've got a top and a base as x squared, and you've got 4 sides of 4xh. And if I'm trying to find the minimum surface area, it's this area equation I need to differentiate. It starts off as being 2x squared plus 4xh. I need to use the volume equation. Now I was given the volume was 64, and so rearranging the volume equation gave the expression h is 64 over x squared, which I've been able to substitute in the next line down to give a equation for area all in terms of x. So here's my equation for area, differentiating, and to find the minimum I'll put that equal to 0. So differentiating 4x, and I need negative 256 over x squared equals 0. So I found the expression for the dx, and I need to solve that. A little bit of algebra, rearranging and simplifying. I get x equals 4. Now x equals 4, I'm going to have to put that up into the equation for h, and I end up with h equals 4. And that's the proof that it's a cube. You couldn't assume that in the first place. Dimensions are 4 by 4 by 4, and to show it's a minimum, we need to find our second derivative. And again, using 4 for our value of x, we come out with a positive value for the second derivative. Positive value means it's a minimum point. Question 2a. We need to be able to recognize when to use product rule and quotient rule. This is a product because we have x times square root x plus 1, 2 different expressions for x. Product rule, write down the first, differentiate the second, plus write down the second, differentiate the first. And square root x plus 1 is x to the power of a half. Differentiate becomes a half times x plus 1 to the negative a half. To find where a function is decreasing, I find the gradient function by differentiating, and it's decreasing when that gradient is negative. The expression 1 over 2x plus 1 is the same as 2x plus 1 to the power of negative 1. So when I differentiate, the negative 1 comes out the front, 2x plus 1 to the negative 2, times 2 from differentiating inside the bracket. Now the gradient then is negative 2 over 2x plus 1 squared. The 2x plus 1 squared part of that fraction is always positive. Anything squared is positive. And so their overall fraction, negative 2 over a positive value, will always be negative. You've always got a negative over a positive. That means for any value of x, that expression is negative. And so in the question, it's going to be always negative. It's also negative when x is bigger than negative 0.5. And so that tells us the function's always decreasing because the gradient is always negative. Question C, another product rule question. You've got square root of x and log x. If it's a stationary point, then we're going to get a gradient equal to 0. First step is to differentiate y equals square root x log x. So write down the first, square root x, differentiate log x, 1 over x. Write down the second, differentiate the first. Now at my stationary point, that gradient has to equal 0. Now there's quite a bit of algebra happening in this next couple of lines as we simplify and solve. Square root x times 1 over x simplifies to just 1 over square root x. Think about it, you've got x to the half over x to the power of 1. So that subtracts to give x to the negative half, or 1 over square root x. And you've got a half times x to the negative a half times log x. Log x over 2 square root x. The difficulty in this question is nothing to do with differentiation, it's in the algebra where you need to solve it. The next step is going to be to get a common denominator, and when that fraction equals 0, it's the top line, the 2 plus log x that equals 0, and hence 2 plus log x equals 0, or log x equals negative 2. And if log x equals negative 2, go into the power statement, x equals e to the negative 2, or 0.135. Now, our limits question. Quite hard to see the graph this time. I think it's just the little section from negative 1 to plus 1, that small diagonal line, then the curve and the 2 straight line sections. At x equals negative 2, there is no equation, and so there is no limit. When x equals negative 1, it just finishes at a hollow circle, that's the end of the line, so there's no limit. At x equals 0, there's again no limit. Now this part we can sort of understand a bit better. Coming from the left hand side, as the line gets closer to x equals 0, it's approaching that point 1 on the y-axis. From the right hand side, as the curve gets closer to 0, it's going up towards infinity. They don't meet those two arrows, so there is no limit. At x equals 1, from both sides of the curve, the two arrows coming down closer and closer to a height of 1, a y value of 1, that's the limit. So when x equals 1, the limit is 1. Similarly, at x equals 2, both sides of the curve, as we come across from the left or the right, they're both coming to the same point, and when x equals 2, y equals 2, so the limit is 2, the value of y. At x equals 2, well, there's no function, so it's not continuous. At x equals negative 1, we've just got a right-hand side of the curve and a hollow circle, which means no value, and so not continuous. At x equals 0, when I'm drawing this from the left-hand side, I've got that straight line coming up to y equals 1, and then I've got to take the pen off, go to the right-hand side of the y-axis, and start way up there at 7 or 8, and start coming down. To draw the curve, I've got to remove the pen off the paper, take it across, and start again. That means it's not continuous. At x equals 1, I can bring my line down, I've shown that with a bit of yellow line, come down to the point and carry on up again, so it's continuous. I haven't lifted my pen off the paper at that point. And again, at x equals 2, I've just taken my yellow line right around the curve. I haven't had to lift my pen off, so it's still continuous. It's only not continuous if you have to lift your pen off the paper to continue the drawing. And a curve or function can't be differentiated at any of the points where it wasn't continuous, so for any of the values in part 2, but also at sharp points, which means we can't draw a unique tangent. So it's the same answers as part 2, plus x equals 1 and x equals 2, because of those two sharp points. Question E looked a lot more complicated than it actually was. So we have the equation y equals e to the negative x sine x, which I differentiate using the product rule to get dy dx, and then I'm going to differentiate a second time to get d2y dx squared. And again, that's another product rule, and just differentiating, collecting terms, we end up with negative 2 e to the negative 2x cos x. So I've got an expression for dy dx and d2y dx squared. So I substitute those two expressions, dy dx and d2y dx squared, into the equation given at the start, the radius of curvature. And you can see I've done that down here, and replaced the x throughout that expression with 0, which eventually simplifies down to giving r equals square root 2. Just the one little thing, on the denominator it's got those straight brackets. That means absolute value, which is the positive answer. So although the inside expression comes out as -2, the straight brackets mean positive, so it becomes positive 2. Question 3 is quotient rule. So each question, 1, 2 and 3, is used either product rule or quotient rule. We need to be good at those. Just substituting and differentiating using the quotient rule, and we come up with dy dx. Find the stationary point, find the gradient function, dy dx, and put it equal to 0 to make it a stationary point. Differentiating x plus 1 over x minus 1, I get 1 minus 1 over x minus 1 squared. Now that equals 0. Now there's sort of a standard approach to come and solve that. The first step will be to take the 1 over x minus 1 squared to the right hand side, and I've done that because then I can cross multiply. I've got two fractions, 1 over 1 and 1 over x minus 1 squared. I cross multiply and get x minus 1 squared. When I take the square root, I lose the square on the left hand side, it just becomes x minus 1, and the right hand side plus or minus 1. And so x equals 0 or -2. To find the stationary points, I use my two. By putting x equals 0 or 2 back up in the original function, I get the y values, which I'm now going to write as stationary points. So I've got to pair them up, 0, -1, and 2, 3. Make sure you pair those together as points. Question C, if you do that function on your graphics calculator, it's quite hard to see unless you expand it quite large, but m is a maximum point. It does come up to a maximum of m and then slowly tapers off to the right. And our maximum occurs when the gradient equals 0. Now this question is a lot easier if we make use of our calculators. Firstly, we have to differentiate anyway, and dy dx from the quotient rule, x minus 2x log x over x4. That's as far as I need to go as far as the algebra is concerned. I have continued doing it there by solving, and if I need the fraction equal to 0, it's the top line that equals 0, so I've solved for 0 equals x minus 2x log x. But I can avoid all that algebra by now going to my calculator, sketching the curve, and using gsolve. F5 for solve, F2 for maximum, and there's my answer there on the calculator, 1.648 and 0.1839. The same as I've got by going through that process of algebra. For this pair of parametric equations, which I need to differentiate to find dy dx, I've done a working box over there on the left hand side, so on the right hand side, that bit in yellow, and that hopefully will give us some examples to see how we differentiate with the constant m in there. So for x equals m minus m cos 2 theta, I've made up the example of x equals 4 minus 4 cos 2 theta, and when I differentiate that, see how the first 4 drops out, it's just a number, and I'm left with 8 sine 2 theta. Well, in the same way, if x is m minus m cos 2 theta, that first m will drop out, just like a number, because that's all it is, just a number, a constant, and I'm left with 2m sine 2 theta. Similarly, part of the expression for y, I've got that first bit, y equals 2m theta. I think if you had y equals 25x, when you differentiate it, you get y equals 25. If y equals 2m theta, and I differentiate, I get 2m. 2m is the number in the same way as the 25 was the number in the example beside it. So when I come to differentiate x, I get dy dx is 2m sine 2 theta, and dy d theta is 2m minus 2m cos 2 theta. Okay. You may have to think about that a little bit, but thinking m as a number. Now I need to substitute those two into dy d theta times d theta dx. So a slightly simplified version for dy dx would end up being 1 minus cos 2 theta over sin 2 theta. Now we're told theta equals pi over 4, and if you did it in radians you'd use radians use pi over 4, and for degrees you'd use 45 degrees. So just make sure your calculator's set on the correct thing. We're going to put pi over 4 into here, 1 minus cos 2 theta, 1 minus cos pi over 2, divided by sin pi over 2. And this comes out to equal 1. To find the equation of a line, we need the gradient, which we've found, dy dx. We also need two coordinates. So I need to bring that value of pi over 4 back up here to the two equations for x and y, and work out what they equal when theta is pi over 4. So by doing that, I end up with my values down here, x equals m and y equals m pi over 2 minus m. That's what I get when I substitute theta equals pi over 4 into the original expression for x and for y. Equation of a line, y minus y1 equals x minus x1, and we get any of these versions here on the left-hand side. So either of these two equations is right, or any equivalent version of them. If the rate that the tank is leaking is proportional to the height, then it's also proportional to the volume. And that's where we've got that little statement, water leak is dVdt. Now, proportional to dVdt means it equals what we call kh. K is the proportionality constant, and dVdt equals the proportionality constant times the change in height. Volume, pi r squared h. Pi is a constant, r is a constant, h is the only variable. When we come to differentiate and find the change in height, dh dt, it equals k pi r squared times h. And h is the only thing that changes in that expression. K, pi and r squared are all constants, so dh dt is proportional to the height.